Hi class, let's take a look at a confidence interval. And this is the idea behind a confidence interval. So it technically goes back to the first definitions that we talked about. And let me actually go back to that one. And here's the idea. Based on a sample, you're going to be able to determine what is the value for the parameter on a population. So for example, let me go back to where we're at. In this case, based on data that was collected, and there's a little bit of probability involved, we're able to determine if it says 90%, we have about a 10% error that the mean salary for some population is between these two values. So within a 10% error, we can quotations guesstimate, in this case, estimate that, well, the mean or the average for the population is between those two. So all of the confidence intervals will have some sort of an error, and this is because, well, you only have a point estimate, which is technically the mean of the sample. Now, this is related to a hypothesis test. In a hypothesis test, the researcher has an idea because they probably seen the data and they can infer that a parameter may be greater, equal, or less than a specific value. Once we run the proper test, then they can actually estimate that, well, in this case, same idea as the previous one. Within a 10% error, they can estimate that the mean salary is less than 60,000. So it's basically an idea that the researcher has. There is a specific procedure to test it, and then they can basically conclude if the value for a parameter happens to be equal to a specific value, less than or greater. But it's an idea that a researcher is able to observe from the data set or from previous data collected. Okay, so we're going to start with a little bit of chapter 2. And in chapter 2, the basic idea is you're going back to samples and populations. Now, if they mention distribution, you're looking at a population. If they mention basic graphs, for your basic graphs, you're looking at the samples. Now, what you're going to be seeing in chapter 2 and on is the type of distribution that you could have. So the first one is the bell shape or normal. And theoretically, your distribution goes on to infinity. So technically, you're supposed to have arrows there and there. Since you're looking at, well, most of the populations here and technically very few on the extremes. When they're talking about flattening the curve for the cases of COVID-19, this is what they're referring. They're looking at as time was progressing back in, well, for us, back in February, it was actually spiking. What they want to see is that it reaches a maximum value as time progresses. New cases of COVID-19 decrease, and we want those to basically go to zero so we can go back to normal life. Okay, let's take a look at the next distribution. And the next distribution is called the uniform. Now, the basic requirements for a uniform is that it basically has some sort of a square or rectangle. And within the square or rectangle, you have all the values of the population. And you could technically have multiple rectangles. That's a possibility. Now, a cousin of the actual bell-shaped distribution, it's basically a distribution that happens to be skewed. Now, for the skew distributions, they're labeled based on the tail. And the tail refers to the extreme values. So for example, if they were to mention that the distribution is skewed to the right, they're referring to the tail has an error on the right, and extreme values will show up on this end. You have most of the values to the left. Any outliers will be actually out here on the right. So skewed to the right means the tail is to the right. Extreme values will be to the right. And, well, not to confuse it with skewed to the left. On a skewed to the left distribution, most of your values are to the right and the tail is to the left. Now take a look at all the distributions together, you can see the bell shape in the middle and then the skew ones next to it. Back to the idea of why we call this science. This is because of the following. We may start collecting data and the data appears to be bell-shaped. As time progresses, then they may realize that, oh shoot, it's actually skewed. And well, as we keep collecting data, they may end up concluding that it's not skewed to the left, it's actually skewed to the right. So in statistics, everything's changing. You can think about your age. You're not going to have the same age today than 3 years later. So it's always changing within time